Well, it's 7 o'clock. Welcome back, folks. Well, here's my announcements. They usually get wiped out as we have to reshare the screen. But so far for announcements, nothing too major. We have quiz 2 coming up. We're about to finish off section 2.5. And this is the related definition that goes along with it about continuity. But even more exciting, we're getting close to defining the derivative, which is going to justify all this work on limits that we've all been working so hard on. So that's an exciting point. And maybe even more exciting is we have our first upcoming exam just about ready to go. I've nearly written that exam. And what I'll be doing after I do write it is I'll be sending it first to the Pocatello Testing Center. I'll also send a roster, and they'll be reaching out to students who test in Pocatello to schedule the exam. I'll initiate that contact, and they'll be working with you throughout the week to schedule. But before we go any further with the announcements, any questions at all so far, folks, about the upcoming exam? Okay, let's just go through maybe kind of a standard run through of things that we might say. Let's see here. Oh, there we go. First thing to mention is there's some good sample exam 1 problems indicated both here and here. These ones are, let's see, the blanked out lecture notes, but it's all in one spot. So you could use this as just a whole sequence of worksheets. These are problems that we should still be able to solve cold. And if you can do that, if you can solve every one of these cold, then you're doing great and you will be considered well prepared for the upcoming exam. So that's the first document you could take a look at. On the second document, version 2, for this one, you would want to go to your book, the online version, and you can go from a section by section basis. I selected the problems that to me look like good additional supporting questions as well. So there's now multiple ways that you can review for the exam. You can go to your WebAssign and practice those problems. Sometimes you can practice another version, but that is unreliable. Some of the problems only have one version. You could go here to get additional problems, or we could go here to solve some of these that we've seen before. And even still, if you really want to solve more problems, this is the sample final exam list. This is like a humongous test bank for all the sections we intend to cover. So you'd want to not study the whole thing, just go to the sections that we're studying for the current exam. And what are those sections? It's going to be, for the definite coverage, these specifically. I'm not going to put any extra, take any off. So we're going up to continuity. Any questions at the moment, folks, about the upcoming exam? Okay,
Really
so it's good.
quickly. So I might have just missed it because I jumped on just a second late. But so there's
No
those
worries.
sample problems. Is there like a key for the right like answers for those anywhere?
Sort of. Let me go through them. That's a really good question. Thanks for asking it. So for this one, because these are the blanked out lecture notes, you could go to Moodle and just find the corresponding section. And it's the same exact problems with the solutions that we wrote in. So that's kind of the key for that one. For the second version, hang on, let's get organized. So that's the first version. It's just really blanked out lecture notes. This one is problems out of your textbook. And so when you go to the textbook and look at those problems, I try to look at exclusively odds. If you see it even there, it was just a really good question. And because they're all odds, you can just click on the problem see answer button on the book, and it'll let you know if you're on the right track with those. So this one sort of has a key. It doesn't have this full step-by-step guide, but you would know if you're on the right track with these problems right here. And then finally, for the last set, this one is found at the very bottom. This is review for the whole course. This one does have an answer key at the very, very back. I thought, hang on, let me take another look. Sample final exam problems. And at the very back, it's not a good one to print out unless you're just not worried about it. But yeah, there are answers, complete step-by-step guides on the very end of that one. So there's answers for that one. And these are really book problems with odds. Other questions about that at the moment? Okay. Going forward, well, we know the definite coverage is the sections. The exam is closed notes, but there are certain things I'm going to be including on all the exams. So when you go to study for our upcoming exam, and I'll try to get this out a little bit earlier. I felt like that should have been provided probably as we were going to weekend last Wednesday. These are going to be the notes that are provided on the actual exam. This is going to be your last page of exam 1. You can tear it off if you'd like, work your exam and this page of notes side by side. You can also flip it over and have scratch paper on the back of this one. But that's what we'll be doing for the upcoming exam. You're not necessarily required to memorize every single thing about calculus. And this is a document of things that will always be provided on each pertinent exam. Let me state that better. This is the sheet that will be provided on exam 1, and a different sheet will be provided on exam 2, and a different sheet for the final exam as such. And you will know if nothing is provided here, any formula or thing that's not provided here is something that we should memorize for the purpose of the exam. So the first exam is always kind of the most nerve-wracking one because we're getting used to how it's going to go, style of writing the questions, and that kind of stuff. But after we get through this, it's pretty much going to be a repeat of this process. My exams are open calculator, not because I'm trying to write in questions that requires you to estimate left and right on every single problem, but more of just a reassurance. And when we do an applied problem later on for exam 2, we'll already be ready to go on the calculators. For these exams, it does have to be specifically those two calculators. So this is the TI-30XA that you'd probably use in like a lab class, maybe chemistry or something. But I would recommend this one. It costs like $2 more at Walmart or something like that, and it has more creature comforts. But I think it's my full spiel, folks, for the exam. Any other questions at the moment? Okay. If any questions do come up about the exam, don't hesitate to interject at any point. And for the moment, we're going to go back to section 2.5. We have our quiz 2 that's going to be due next class, and I'll get the quiz 3 posted before we come back to next class as well. But as far as continuity goes, this is pretty much it right here. On our announcements, we say a function f of y equals f of x is continuous at a number is essentially saying we have direct substitution for that function. We take the limit as x goes to a, well, we just plug a right exactly here. And continuity is saying this is always allowed. So as a set of formulas or a limit process, this is what it looks like. But as terms of a graph, which is equally important to see it both ways, both graphically and as a limit, continuity looks essentially like this. It's one unbroken curve. You can draw a continuous curve by never lifting up your pen and dropping it somewhere other randomly on the page. So there can't be any holes like this one. There's our removable discontinuity. Can't be any vertical asymptotes. That'd be even worse. Jump discontinuities. There's all sorts of wild behavior that we're trying to exclude. But if we know we have continuity, for example, if we just know that that's a polynomial and polynomials are continuous on their domain, this is what continuity looks like. That limit when you're plugging in 0 just means directly substitute in 0 and you get that output of -8. So that's what continuity looks like, and that's how we ended class last time. Any questions so far, folks? Okay, here's where it gets a little bit tricky. We have single-sided limits, and that means we also have a notion of single-sided continuity. Here's what it looks like as a statement of two different limits. Continuity from the right means the limit as x tends towards a, but coming in from the right exists and is equal to f of a. That means you're continuous from the right. And if you say continuity from the left, that means the limit as x approaches a, but from the left of a, so all numbers lower than a, would also have that direct substitution. So as a statement of two limits, it's not too bad. It makes sense, right? Continuity from the right, put in the plus sign here. Now it's a right-hand limit. But actually seeing it as a graph is a little bit trickier. It's kind of surprising. So let's do a pretty big graph on this one. Let's take just about the maximum of the horizontal space we have. We're going to put some issues on this curve. First, let's go left 1, 2, 3, 4 units. On the horizontal axis, let's get a height of 1 and 2. We're not going to go too crazy. So at -4, I'm going to first put in solid dot, then an open circle right above. Let's also do something at -1. For -1, let's put in 2 open circles. And that's it. The function is now going to be undefined at -1. And let's go over here at 3, so the picture is not too busy, and 2 more dots. Let's do a solid one and an open one. It's a random drawing, so the placement of all these points is also random, and I forgot to do one thing. Let me put that solid dot by 3 at a height of 2. There we go. And this one looks like it's at a height -2. I don't think I thought my way through all of those points, but let's start drawing the curve next. So this is one curve, y equals f of x. For -4, let's let it come in and approach the solid dot like that. Now it's just plummeting to the left. As it proceeds to the right, we're going to let it come in and move this way, approaching the top dot. Now from the left, let's see, let's go from open circle to open circle. Now on this one, there's not much more I can do with it, but let's maybe let it do something like that. Looks like it's approaching an asymptote on that one. So there's our curve, and now we have several discontinuities. We have a jump discontinuity at -4, a jump at -1, and a jump at 3. And the reason we're focusing on jump discontinuities is that's when you typically have these kinds of continuities. If you're continuous only from the right or continuous only from the left, you're expecting a jump discontinuity. Now, to me, this is maybe me personally, but I feel like this is pretty tricky. This is continuous only from one direction. Has anyone spotted the direction? Is it only from the left or only from the right? Good call. This one is continuous only from the left this time. One way to tell is continuity from the left means as you approached, you hit a solid dot. If that was open, it would not have been continuous from the left. That's a lot to train your eyes, so sometimes it's easier to see it this way, analytically, just looking at the limit statement. Let's see if we can make this limit statement, let's click the correct one, continuous from the left. Let's see if we can make that limit statement actually work, where we believe, and it's true, that is continuous only from the left. We would take the limit as x tends towards -4. So we're heading in this direction. But if we're coming in that way, we need to put a superscript of a negative sign above to say, now we're coming in from the left. It's for a function f of x. And now let's see what happens here. It's going to get higher and higher and higher until it approaches a height of 1 right here. So I put 1 in the middle, and then now a new equality. 1 happens to actually be equal to f at -4. So if you plug -4 inside here, because of the solid dot is lower at height 1, this is what gives us continuity. There really was a direct substitution. I have an extra number in the middle to show the limit was equal to the function. So I'm circling the wrong one again. We have equated this side, the left-hand limit, with the right side, the function. It's okay if you have a number in the middle to show that they link up through equality. So that tells us immediately right here, continuous only from the left. Because when we come in from the left, that limit statement works out. If we did the limit statement coming in from the right-hand side, however, we would have gone limit as x approaches -4, put a plus sign to say you're coming in from the right of f of x. This is approaching a height of, well, it looks like maybe 1.5, which is not f at -4. F at -4 came out as a 1, so this breakage right here is the reason it's not continuous from the right. So not non, that's French, not continuous from the right. So it's sometimes a little tricky to pick it up on the graph. If you like the analytic way of writing out the limit, that's a foolproof way to do it. But eventually, it's not a bad strategy to really train your eyes on this. Continuity from the left means you're approaching in the left direction, you landed on something solid. So over here, there is no continuity from the left nor the right. One of those dots would have had to have been solid to make it work. So let's say no continuity at x equals -1. We've lost any ability to do that. And even if we redefine the dots, say, in a weird spot at height 1, still there's no continuity from the left nor the right at all at -1. You have to fill in this dot or this dot to get a single-sided continuity at that spot. Finally, last one. When we come in from the right-hand side on this curve, we hit a solid dot. So this tells us at this location, this is what continuity from the right, or continuous from the right, looks like. So we have continuity from the right, continuity from the left, and neither. Let's make that kind of pop a little bit better. Continuous only from the left, neither. And this one's continuous only from the right. Well, after drawing these out, this is pretty much the situation. Any questions at all, folks, about single-sided continuity? Okay, now that we've got those pictures, for continuity overall would mean the single-sided limits both agree from the left and the right. And now let's take a look at this function. Like before, it's the graph of one single curve. It just has multiple issues with this. First thing we're going to do is just to take a tour of the kinds of discontinuities which are we're going to commonly see in this course. So we'll state the numbers where the graph is discontinuous. We could start off by saying x equals 1, for example, is definitely a discontinuity. I'll also state the type of discontinuity as we see it. So right on this one, any volunteers for the type of discontinuity? There's
Is that
kind of a hint on
just
this.
a gap?
Sorry,
Is it a
Andrew,
gap?
I talked right. Sorry, say again.
Is it a gap discontinuity? I can't remember the exact term, but something like that.
Uh, how would you explain that one? That's kind of a new terminology for me as well.
I guess just because there's a hole, it's not like a jump discontinuity, but there's just the hole right there. I can't think of what the exact name is.
Gotcha. You're on the right track. So this is one of those continuities where you could fix the function and make it continuous right here. If you did a 1-point change, you would go like this. The function is now fixed, and that means this one's called removable. Not because we're actually changing the curve or putting in a new point. We call it a removable discontinuity because you can remove the discontinuity by just defining a point or redefining a point. So this one is the removable one. Does that make sense to folks at the moment? Awesome. If we go to the next portion, x equals 2, same idea. We could remove the discontinuity here by taking the one single point and just put it right there. That would give us continuity. So this one's removable. Then this one requires a little bit of consideration. How do folks feel about this one? Is this a discontinuity or not? Some are saying no in class. How about folks over in Zoom? Does that look like a discontinuity?
I think that one looks continuous.
Good call, folks. Yeah, that one's actually just totally fine. But if you felt suspicious about that, if in your gut you knew something was just a little bit weird, in one sense, you are right. Not an issue of continuity. Continuity means you can draw the curve without ever lifting up your pen, but that's a really sharp point on the graph, and it does require some special attention. It's continuous here. All right, so it's continuous, but not differentiable. We're going to define the derivative right after this section, so it's good to know where a derivative fails to exist. It would fail to exist here despite the fact it's still continuous. So a function that's differentiable is not only continuous, it's also a smooth curve in a certain sense. So That's a special point to pay attention to, although it doesn't fit the question. It's definitely continuous there. Then when we get to this one, this is the type of discontinuity that we were just looking at, right? It definitely jumped from, well, jumped down from a height of 2 to a height of 1 right here. So we can say at x equals 4, this one is a jump. Almost there, folks. One last discontinuity at x equals 5. Anyone spot the type of discontinuity here?
I think we just call that an asymptote, right?
Exactly. I think that'd be a great way to say it. And that's really the whole issue on this one. There's an asymptote, it's a literal barrier to the function. And so you could either say x equals 5 due to an asymptote, or you could call an infinite discontinuity. But if this was a real question and you put, say, asymptote here, vertical asymptote, I would include that for the right credit because you are absolutely in the spirit of the problem. Vertical asymptote is implying a discontinuity as well. What we did, folks, I thought those are the discontinuities. And these would be the ones I might ask about on a real exam. There are still other wild problems a function can have, but these are the main ones that we're looking at. Any questions so far? Okay, now we're getting to the new stuff about single-sided continuity. It says for each discontinuity stated, we might as well list them out. It's referring to x equals 1, x equals 2, x equals 4, x equals 5. Okay, so there they are. For each discontinuity, determine whether f is continuous from the right, the left, or neither. All right, let's try this out. How about for x equals 1? What kind of continuity would you say we have on that one? Oh, geez, right out of the gate. That one's kind of tricky, I think. It wouldn't be continuity to the left on this one. It turns out this one, I'd start off with a tricky one. It has this weird feature where f at 1 is undefined. That's another thing to look at for this. If the function's undefined here, we have no notion of continuity, not double-sided from the left or from the right. It goes back to this statement right here. The moment you write that out, this has to exist. We have to have a f of 1 right here. If it doesn't, or if the limit doesn't exist, or if there's no equality, we've lost continuity. And if we've lost that kind of continuity because f is undefined, we've also lost these kinds of continuity. These both have to be defined to get either side of continuity. So sorry about that. That one turns out to be kind of the nastier one of the set. If you see something undefined, then this would be neither. Does that make sense, folks, on the issue here? Awesome. It gets even worse because over here, f of 2 is defined, but this one's still a tricky question. Single-sided continuity means when you come in from the left, our limit should output a 2 for direct substitution, but it's not. It's outputting a 1. If you come in from the right, our limit gives us a 2, but the function drops down at 1, so this one is also a neither as well. Well, so neither on both of those, but once we go to 4, right here, this one does have a single-sided continuity. Anyone see which side it should be? Good call.
Right.
When we come in from the left, we hit a solid dot. So it turns out this one would be continuity from the left right here. Let's say from the left. How about we pause on that one and let's see if we can show it with the actual limit statement, because these are always pretty tricky. If we really have x equals 4 is continuous from the left, we should be able to do this. Limit as x tends to 4 from the left of the function f of x. Let's first see what it turns into, and then we'll compare it against f of 4. We are hoping we have equality right here. So first is the limiting process. We're heading towards 4, coming in from the left. Visually, it looks like this. We're walking up the function until we get around here and observe the heights are getting closer and closer to 2. Next, for continuity, we have to verify what happens to f at 4 itself, this 4 being the same value from the limit statement. So f at 4, you go to 4, plug it in. We pass through right here, hit the solid dot, and it does output to 2. So that means the limit, as x tends to 4 from the left, resulted in direct substitution. We just plugged in f of 4, and that means we have continuity from the left, all due to that negative sign right there, making this equation work out. So I'd say the bigger takeaway for this example 1 right here is, for looking at single-side continuity, you must have a jump discontinuity to make that happen. So it was continuous from the left, and we knew it was a jump. A jump is not even enough to guarantee it. It was also the fact that it was solid right there is what got us continuity from the left. Then the vertical asymptote, this would also be neither. So example 1's kind of an oddball, but again, the big takeaway is, if you're being asked if something's continuous from the left or the right, look to the jump discontinuities and make sure the function is defined somewhere. Every other discontinuity is irrelevant for that kind of a question. Well, other questions or comments, folks, on that first example 1? Okay, that's continuity so far. It's a very powerful statement. When you know a function's continuous and you know you're taking the limit, say where the value of 4 is in the domain, all you're doing is direct substitution. That means we need to get a feel for what are the continuous functions, and this is going to be kind of the nasty problem for our homework. But I'm not going to ask this question directly on any exams. Think of what we're doing right here is thinking about which functions are continuous so we can use the property of continuity when we evaluate limits. But even before doing all that, let's think about continuity a little bit through example 2 and this next example 3. Example 2 is kind of special for the class, and this is one where it's worthy to mention this. Oh, I kind of already wrote it in, never mind. This question may be asked on exam 1, and it could be asked on the final exam as well. There's 3 big questions: continuity, differentiability, integrability. They all come from a limit, so these would be concept questions that can come on exams. I'll always let you know if there is a limit type definition you should expect. It says, write an equation that expresses the fact that the function f is continuous at the number 5. We didn't say continuous from the left or the right, so we're going to write a double side limit. And this is how it would probably start. Take the limit. If we're asking about continuity at the number 5, that's where x is heading towards in the limiting process. So lim as x tends towards 5. It's referring to a function f. So when we go to write this out, we need to involve the actual function itself. So f of x would go here. On the right-hand side, I mean, everything here is important, really, but the right-hand side probably gets more partial credit than anything else on here because it's the punchline. Any volunteers for what should be written in right here? Exactly. We're going to take the 5 that you saw here. We need to put it into the function, and it goes pretty much like that. So let me fix my color coding. That will make it a little bit more sensible. We take the 5, throw in the function, and you've got it. So that's pretty much the whole statement. It's a weird question, but sometimes when we work with continuity, it is actually easy to forget that you have this equation there. So these kinds of equations are kind of a reminder as well. There's a big statement behind the fact something's continuous. So anticipate that question both on exam 1 and the final exam, and it's a fast reminder to walk through. This is the harder one, and we've seen these kinds of questions before. On real exams, I would never ask more than one, but here's our new updated such question. We have, let's see, 6 conditions we're going for. We're going to build one function that satisfies all of them. Any questions at all, folks, before we start this process off? Okay. Let's scroll down. We'll have to come back to this one, but when it says the function is defined on R, it means we can't have any holes that look like this. That one right there would be undefined right at 1. So we're trying to give the domain everything, no holes in the graph whatsoever. Or no holes in the domain, rather. Could be holes in the graph. We also have continuity only from the left at -1, and a bunch of other conditions. Let's see here. Let's start by putting in the x values to organize. So there's a problem at -1 to start. Jump discontinuity at -3, so -2, -3. If they tell us there's a jump discontinuity there, sometimes the best way to start is just to put 2 open circles on a vertical line right where -3 is, and we'll work out that jump discontinuity. You might want to fill in one or the other, but let's see what happens with the rest of the information so we don't have to delete things as we go. Removable discontinuity at 2, so let's go 1, 2. Removable means there's a hole somewhere, so let's go like that. Infinite discontinuity at 5, so let's go 3, 4, 5. That implies a vertical asymptote. And it says the function is only continuous from the right at x equals 5. This is going to be an interesting one because we often say a function cannot cross a vertical asymptote. That is true. But sometimes we go a little too far by saying a function can't even touch the vertical asymptote. That's not exactly true. It's true in spirit, but you can define certain functions called piecewise functions that breaks that. So this graph will be a little bit odd because of this last 2 statements right here. Well, that's the situation. Let's run through these again. Let's see, function defined on R, so we'll have to make sure to define it at 2. Continuous only from the left at -1. That implies another jump discontinuity, so let's put 2 open circles. And now where it says continuous only from the left at -1, let's draw a curve that goes like this. I need to make the curve head towards the solid dot. That way we have that continuity from the left. If it came into the open dot, maybe we have continuity from the right, but not from the left in that case. So that takes care of this condition here. Let me put a check on it. Let me highlight that a little bit better. I'm going to use yellow highlighting to just denote single-sided continuity where it's tricky. Next issue is jump discontinuity at -3. And it looks like that's what we did. We made it jump. Now we can make this carry off this way if we like. I usually put an arrowhead to convey domain is all real numbers. It's not stopping. It's going to the left that way forever. But I do have an issue at -3. The function is not going to be defined at -3 unless one of those are solid. But you have a lot of freedom here. Let's see. It just said jump discontinuity, so you could fill in one or the other. You could possibly fill it in way up here. Just has to be a solid dot somewhere on a vertical strip about -3. Okay, so we've got one there. Next, we're told removable discontinuity at 2. So now we can convey that. To make it removable at 2, let's just make the curve not do that. That's broken right here. What was the problem at -1? Continuity only from the left. I carry out like this. That's continuity from the left and the right. I broke that condition. Let's delete this one here. We carry down from the lower dot upwards. So that maintains that condition right here. Continuity only from the left at -1. So carry that up. Removable discontinuity at 2 would look like this. To have all real numbers defined, we really need to define a value somewhere with a solid dot. So we'll go right here. You could put yours maybe on the x-axis, anywhere you'd like, on the vertical step around 2. Looks like we've got that one down. Infinite discontinuity at 5 would look like this. You can make it go down or up, approaching the vertical asymptote. And ordinarily, if you saw that, you might put another bit of the curve, maybe going upwards or downwards. But we also need this continuity, only from the right at x equals 5. That's the odd one. We can put, say, a solid dot anywhere, let the curve go out, and that's continuity from the right. We wouldn't say the curve crossed the vertical asymptote, but you can define a piecewise curve that starts at a vertical asymptote. That's as extreme as we can get with these things. So let's take a look at all these conditions. Here we have jump discontinuity at -3. Coming in, that's continuity from the left right here. Then that's our removable. That's the infinite discontinuity. And right here is continuity from the right. That one, in my opinion, is a lot trickier than ordinary. So if I write one of these out for a real exam, I probably wouldn't make it this convoluted, but I think, again, this is always a good one to practice. Reverse engineer a bunch of conditions to get the graph is essentially just an opposite question as what we were doing, well, up here, starting with a graph and then looking at the features of it. Well, any questions at all, folks, with producing that graph?
What did you say it meant that it was defined on R?
Oh, this right here?
Yeah, that one.
Gotcha. Question there, it means there should be, oh, let me put that out of there. It means essentially there should be no holes in your graph that are left undefined. Well, let me make a better comment there. For the function to be continuous on R, we require that f of x exists for all x. In other words, there'll never be a time where you say f of -3 is undefined. So we have to have a point on the graph for every single x value. Does that make sense for that question there?
Yeah, that makes sense. Thank you.
Yeah, you bet. Thanks for asking about that, Andrew. And again, this graph qualifies, but if we took out that point, I'll fix that in a moment, that would be our problem. F of 2 would be undefined, and that would mean the function is not defined on all real numbers. So we essentially have to have an elimination of this. Let's add that to an additional comment. In other words, we should never have a point at which f of x is undefined. Other questions so far? Okay, well, we've gone through our graphical look at continuity. Next thing we're going to look at is a little bit of analysis. So here's how it goes. This is kind of like the limit laws in a certain sense, where the limit laws, it's not about memorizing them all verbatim. It's just being familiar with what you can get away with, essentially. And so here's a long list of things that you can do with continuous functions. So if you start with the statement that you have two continuous functions, you can now build a whole array of new continuous functions based off them. Add your functions, subtract them, scale or multiply them, multiply by some real number, or really multiply the functions or divide, as long as you don't divide by 0 ever. And those are all continuous functions. So that's really handy. Theorem 6 is also really powerful. This is a catalog of functions that we've studied potentially, and they're always continuous. One word of warning in our course, though, is this right here. Not so much as a warning, but potentially something worth mentioning. Trigonometry is not a prerequisite to this class, and so we're not going to cover the trig functions directly. That means these statements I typically do delete from the theorems if they become kind of confusing, but I let it stand on this one. So let's take a look at all the functions. We looked at polynomial functions and power functions and root functions before. So this whole class of functions could be stuff like this. F of x equals maybe cube root of x minus 2. It's automatically a continuous function because we're dealing with, let's see, a root function, that's the cube root. The function inside of it is a polynomial function. And this statement says here, composite functions are continuous as long as you started with original continuous functions. So we have a composition of continuous functions. This one is continuous. When it says a exponential function, we're referring to things like these. F of x equals 5 to the x. F of x equals maybe e to the x would be these kinds of functions. Let's see, rational functions. That's just a polynomial divided by a polynomial like we looked in the prior notes. And also logarithm functions, logarithmic functions. This would be stuff like, say, y equals natural log x, or maybe y equals log base 7 of x, and so on. Those functions are also continuous on their domains. And that means with all the statements we're making, that's almost the hardest part about continuity, or determining if your function's continuous at a value. It's more, what is the domain of your function? That's how you're going to spot if you can use properties of continuities. Theorem number 7 here, I include this one mainly for completeness. We've used it before where sometimes we take a limit operator and commute it inside the function. We don't use that a lot. Again, this one is mainly here for completeness. So I'd say the theorems most important to us, theorem 4, theorem 6, theorem 8, give us classes or categories of functions automatically continuous. And we did mention before, this example 4 is a little bit weird compared to what we've done in the course. I'm not going to ask this one on a real exam, but it's more us just getting familiar with these 3 theorems. So we want to find the domain of that weird function. It involves all sorts of stuff, square roots, logarithmics, rational with polynomial in the denominator. Rational is not quite right because it's just the polynomial in the denominator, not in the numerator. We want to know where that's continuous. That means we need to find its actual domain. So let's begin with that question there. We have a square root function to start. Because there's a square root function, we can begin by saying in the numerator, y equals root x has domain that goes like this, from 0 to infinity. The bracket here says you can put an actual 0 inside there. Comma to infinity says all numbers starting at 0 and larger than 0. So that function is continuous on that set. Then we look on the inside here. If I can highlight that, that's a little bit trickier. Now we're dealing with a natural log x, and y equals that thing. Has domain a little bit smaller. We actually lose a point with a logarithmic function. The point we lose is right at 0. And the way we communicate that is we start with a parenthesis at 0. So now we have excluded it. 0 wasn't in the domain of the natural log function. And then go to infinity. So back to the function f of x, the whole domain shrunk a little bit because we cannot put 0 in there any longer, simply due to the natural log x function. Then we go to this one here. That's like the g in the denominator for the earlier theorem. We need to be wary of that thing because if that obtains a 0, then at the point which it occurs is not in the domain. So let's take a look at one last function. Y equals x squared minus 9x plus 20. Well, its domain is all real numbers, but the reason we're looking at it is we're interested in when that thing is going to output a 0 in the denominator. We can detect that by factoring it right away. So x squared will split as x and x. Positive sign here tells us the middle signs must be both positives. Or excuse me, let me try again. Positive right there means the middle signs must be both the same. They could be both positive or both negative. I should turn this over to the class though. What should they be? Negatives or positives here? Good call. So from positive here, signs are the same. From negative here, they're both negative. So we'll go minus and minus. Good factorization of 20 might be a 4 out of 5. They sum to negative 9. They multiply to positive 20. And so that's our factorization. So now back to the original function f of x. This function, we have to exclude two values. X cannot be 4 and x cannot be 5. So overall, we can now state the domain of the function. It's not bracket 0 to infinity. It's going to start at 0, but then it's going to hit that problem point, will exclude, and will exclude that problem point as well. So in interval notation, we'll say the domain of f of x is start at 0, go up to this point right here. So from 0 to 4, we'll throw in another set. We'll use this union symbol to say 0 to 4 together with, or unioned with, go from 4 to 5. We've skipped across this point now, and then the last bit is going to be off to infinity. So union 5 to infinity. And for the color coding on this, 4 and 5 came from that denominator. 0 came from the fact we were dealing with the natural log, and so did the infinity right here. Yeah, go ahead, Mike.
I just had a quick question. So when you're writing out the domain of f of x is equal to, would you still need to put the other sort of bracket instead of the parentheses at the 0 and the infinity, or would you not need that?
For this function, we would take away the brackets on it. We're putting a parenthesis on 0 right here, because that's one point we couldn't actually put inside the natural log. So the parenthesis is what's excluding it. So yeah, we went from bracket down to this only because natural log. And on the upper end, the parenthesis there is only because infinity is not actually a real number. If we put a bracket on it, we would be saying x could take on a value of infinity to throw in there, but it's not a real number. There's no notion there. The parenthesis just says all numbers to the right of 5, never stopping. Does that make sense for that question there?
Yeah.
Awesome. Thanks for asking about that.
Yeah,
Other
no worries.
takeaways about this is a parenthesis will always be associated with infinity no matter what. So whether it's a positive infinity or a negative infinity, and parenthesis here only if you have to exclude a value. Other questions so far? Okay, now we're going to decide, is this function continuous on its domain? You know, it's pretty fast. It says use theorems 4, 6, and 8. And you might start by saying, well, that function right here, y equals root x, is rational. Next thing you might say is y equals natural log x is logarithmic. And so they are continuous. I'll use CONT to abbreviate continuity. Then here's the big theorem 8. If you have continuous functions, you can form the composition of them and still have a continuous function. We have to be careful that we're taking this domain right here because the composition goes this way. Natural log goes inside. We're excluding 0. So we can say now by theorem 8, y equals the square root of the natural log of x. That composition is continuous. So in other words, you can put a continuous function inside another continuous function and maintain continuity. So we've explained why the numerator is continuous. The denominator is a polynomial, so it's continuous. Let's pen that in. The denominator is a polynomial. And so it's continuous. That was by theorem 7 that had a catalog of continuous functions right above here. Then the last thing we do is that's a fraction of a continuous function in the numerator, continuous function in the denominator. We excluded those values from the domain. And so we can say overall, let's put this little triangle to say, therefore, f of x is continuous since it's a ratio of continuous functions. Deserves an exclamation mark because now we can say, pick any number you would like in this set. That's the domain. In other words, don't pick a 0, 4, or 5, anything larger than 0 that's not those numbers. You're in the domain, and that limit can be done immediately. Kind of a nice little process. Well, any questions at all, folks, with this kind of a weird example for today? Okay, sometimes math just gets this way. It becomes more wordy than numbery. And if you like this kind of stuff, then you ought to think about a career in mathematics where you'll do more and more of it. But these kinds of problems are not the objective of the course. If we ever do something like this where we just have to write stuff out, it's only because we're trying to think about these theorems and absorb them through our work, not because they'll be repeatedly asked. Well, one takeaway finally is, let's suppose we were doing a limit. We're going to do that down below, but just to drive that point home, let's do a special limit right here. Let's take the limit as x tends towards any number in this set. Let's pick something nice just to not be too hard on ourselves. Let's pick a 1. That's a great choice here. Limit as x tends towards 1 of root natural log x divide by x squared minus 9x plus 20. So my claim is that's a pretty much immediate limit. You can almost look at it and get a number. The reason is we did all this analysis to determine it's continuous. We picked a value 1, which is in the domain of the continuous function. And so here's what we're going to get. Throw a 1 right there to start. It's root natural log 1. Throw it down below, so it's a 1 squared minus 9 times 1 plus 20. And we're well on our way. Natural log of 1 is a 0, so that turns into square root of 0 in the numerator. But square root of 0 is still 0. So we have 0 over 1 minus 9 plus 20. And so the whole limit is just 0. There's nothing further to do. It's as if the analysis right here was the real work, and continuity is just a formality right here when we go to write it out. Well, that's why we like continuity. And so for example 5, we're just going to evaluate even more. One thing I won't do, like I mentioned, is if I asked you to evaluate these kinds of limits, well, if we're going to use continuity, we're not necessarily going to try to find the domain like this. We're just going to test if it works. We'll try to use direct substitution. If it fails, well, this wouldn't be a correct question for the continuity section. Well, it says to start, take the limit as x tends towards 0 of this weird looking function. Observe if you put 0 in the denominator, you're not dividing by 0. If you put 0 here and here, you get negative divided by negative in the square root, which is positive. It looks like we're all set. We really are in the domain. So here's how this one would go. It's square root 0 squared minus 4 divided by 2 times 0 minus 9. We just took that 0, threw it here and here, and the process is nearly complete. We still have to simplify that as a number, but we're nearly there at that stage. It has to start with the limit operator, but we drop it right here because we now sent x towards 0, so we wouldn't write it in at that spot. So over here, we're going to end up with root 4/9. That's after canceling the times zeros and the negative over negative. Then the root of 4 is 2, the root of 9 is 3, and the whole thing settles down at a 2/3. As fast as you could do it, that's how this limit would go. Any questions, folks, with this one? Okay, it seemed weird to just do one problem, so I have a few more. These don't take too long at all, so let's try it again. This one's an exponential function, which we know to be continuous. Zoom in on that a little bit more. Inside the exponential function is also this thing, x squared plus 1. That's polynomial. It's also continuous. And the function in the middle, that square root, really hard to target. Well, it's a radical function. It's also continuous. So as long as you can plug in 0 and get a real number, your work is done. Let's check it out. 2 to a really weird looking exponent, square root of, it'll be 0 squared here plus 1, turns into 2 to the power of just a square root 1, which turns into 2 to the power of 1, which is 2. Try to take the most steps possible, and it's still a really fast problem on this one. So that's second limit down. And one last one to go. This one is a rational function. We could have done this one in the prior section where they gave us a set of direct substitution properties that worked for polynomials and rationals, as long as 4 is in the domain. If it's not, we might have to factor some other algebraic technique like we did in the prior section. But there's no way to make a 0 in the denominator, so we have continuity, and this is how it goes. Directly substitute 4 everywhere x occurs. 4 squared minus 4 plus 10, 5 by 4 minus 1. It's going to give us in this numerator 16 minus 4 plus 10, and then the denominator we have 20 minus 1. Let's see, 16 minus 4, we're at 12 plus 10 for a 22. You have to like prime numbers. 19 means this one's not going to reduce. And this is where you just leave the answer at this stage. Well, we did it, folks. That's 3 limits really fast. We've done 1 limit that took like 3 times as long as this so far. But the thing to impress upon us is that's what continuity does for us. It makes limits extremely nice to walk through. Any questions at all, folks, with the conclusion here? Okay, well, I felt we were going to end a little bit earlier today, so we now have the major goal for the course. Let's define differentiability. After we define it, will probably be a good stopping point, and we'll take a look at it a little bit more carefully on next class. But this is the content for exam 1. The reason section 3.1 won't be on the exam 1 is only because I like to give a little bit more of a turnaround where you have a chance to do WebAssign, ask questions in office hours, ask questions on a quiz, maybe get your quiz back and that kind of stuff before you see it all again on exam 1. So this is the first section that's going to be on the next exam 2. Let's take a look at it. And here's how it starts. Doesn't give us much, and if you read the textbook already, you'd already see nice, beautiful graphics. But when it comes to learning mathematics, a lot of it's visual. I mean, this doesn't look like stuff we're meant to understand as humans. We need an analogy or analog to that, and anything visual is great. Your textbook, imagine this is your textbook, is going to print out all these beautiful graphics that you have to read and look at carefully. You should still do that. But what I would propose is, when you're studying this stuff, if you come back to an old definition, look at just this part and try to do the illustration yourself. If you can illustrate that definition, then you are definitely absorbing this material very, very well. So let's do that ourselves. Let's try to illustrate everything we see here, first reading it. That tangent line, that's something we'll have to define, to the curve of this function at a point, a f of a, is the line through that point P with slope. You must have that slope specifically. Notice that there's a limit involved there, provided that this limit exists. We are later on in these notes going to call this whole thing, which is a true slope, the derivative. Math is weird, but we're suddenly just talking about slopes again, like you might have done in an introductory algebra class. So let's draw out a graph to begin. I'll leave the function in black so our color coding doesn't get too out of control. We do need several colors. And I want a specific shape just so it's easier to illustrate. Let me make this a little bit more targeted. Let's focus on quadrant 1. We have a curve that's going to go up kind of like that. Okay, so we've got a function y equals f of x. Still don't have the tangent line. The next important process is the point at a f of a. So let's put maybe a point right here. So go vertically down. And this is your input to the function a. Go horizontally to the left at this point, and that's going to be your output, f of a. And this location is just the point P that's being referred to, P, A, F of A. Let's draw the tangent line next. A tangent line has to have certain features where locally, my line is going to be a straight line like y equals mx plus b. And it's going to be the best approximation you could give right at that point by a straight line. So if you were to draw that out, first let me draw it incorrectly. That's a terrible approximation to the curve. I mean, it is going up, but aside from that, nothing here is matching up with the black curve, y equals f of x. And if you zoom in on it, I mean, it doesn't resolve at all. They're definitely not the same. When we define our tangent line, we're going to be able to go into Desmos and actually zoom in and show the further you zoom in, the closer the curve and the tangent become actually the same. It's going to be the best local approximation, meaning the curve should be more like this. It's hard to draw perfectly, so I might do a couple tries, but now I'm trying to do it for real. I missed. That's okay. That's about what my tangent line would look like if it hit it just right. Let's see if we can manipulate this thing. It's actually got to go to the point right here in black. And you know what? Well, let's give it a slight tilt. It's our first one, so we're trying not to mess it up. I think that looks like a pretty good tangent line at that stage. This is y equals m x plus b. And that m we're referring to is this one right here. That's going to be the slope. Now observe how sketchy this looks like based off your algebra training. We were told repeatedly you cannot calculate a slope based off a single point, and that is still true. So we need to find a way to do it somehow, some way, or else calculus is at jeopardy at this point, right? What we need is not the tangent line. The tangent line is the goal. We need a way of getting there. That's going to be the secant line. Let's use green to show it. So the secant line is going to now do this idea. Notice how weird that limit looks. If I need 2 points, we manufacture an additional point. This is where h comes into play. We're going to go somewhere over here, a plus h. Because I wrote it to the right, this is implying h is positive. It could actually be positive or negative. There's no plus or minus on that 0, so we're approaching from both directions of 0, from the positive end and the negative end. I put it here so I just have one sketch to work with. So it's important to know a plus h could really be over here in a different sketch. Once you go over here, you have a new point on the curve. Go directly upward. We're up to that location. Go directly to the left. We're about here. Here's f at a plus h. Let me try to fix that turning though. F of a plus h is at that height. I ruined my arrow. Let me try one more time. This is a good picture to try to get right. So now that we have this point here, we draw a line that goes to the black one and the green one. This is the secant line. And on the secant line, we have 2 points. So our problem in algebra has been resolved. We can calculate the slope of this secant line. And let's imagine what would it look like. The secant line has slope m, referring to a different m here. So think of this as a different scope. So if we're calculating the slope on this one, let's just go to our algebra training. It's between these 2 points. We subtract the y values. So f at a plus h minus this f of a. We divide by the difference of the x values. We will take a plus h, then minus this value a. So one of the reasons why the limit above looks mysterious is because there's a cancellation too. A and negative a are getting wiped out on this. And so that's the slope of the secant line. M equals f at a plus h minus f of a all divided by h. And in a college algebra class, if you were wondering why are we studying these things, it's fun algebra, it's compositions, all sorts of stuff. But this is the difference quotient. Which is required machinery for us to calculate that, the slope of the tangent line. So this is a tough picture to draw because what you really want is an animation or a movie. The slope is not quite right, but you know how you can improve that slope? You want to take this green dot right here and move it closer and closer to the black dot. We can never let it actually hit the black dot, right? Then we're dividing by 0 the moment you did that. But you can get as close as you like on either side. That means you're taking this limit as h gets closer and closer to 0. Those 2 points get as close as you want to overlapping, never truly overlapping. These limit statements start to change, and this line that's green turns into the one that's blue in the limiting process. That means the only thing missing right here is the limit as h tends towards 0. Take that limit and you've got a derivative. So we can finally say the derivative of f at a, let's say x equals a, just to be more specific of where a is going, is the slope m of the tangent line to y equals f of x at x equals a. That's a longer statement than I thought, but there it all is. And what's the physical intuition behind this to think about? Imagine you're driving home, you look down at your speedometer, you are actually looking at the slope to the tangent line, an instantaneous rate of change. That's a derivative already. Tons and tons of examples are really just slopes. That's what differentiation is getting for us. And if we turn everything about this on its head, in a certain sense, literally reverse all this process, we're talking about the fundamental theorem of calculus and doing integration. That one's concerned about areas instead of slopes. So all these weird, interesting things we studied as we learned mathematics, we're just delving into them even further. And the derivative is a way to get slope, instantaneous rate of change like speed, even when you're truly dealing with 1 point. Limiting the process lets us get there. Any questions at all, folks, with getting through that diagram here? Okay, so that's our core definition for what we mean by differentiability. On these notes, we're going to practice it, finding these derivatives by scratch, sketching their tangent lines and such. These are pretty hard problems, so my best advice is don't get too discouraged in section 3.1. There's a fantastic amount of algebra here, but in section 3.2, we're going to find formulas that simplifies the process. This is just the definition that starts everything going for derivatives. Well, I think I ran out of topics to discuss. I mean, we have more, but this is a 15-minute question at least down there. Any last questions or comments then, folks, before we call it a night a bit early? Oh, geez, I didn't even spot that one. I should have. Thanks for spotting that. I think we would. Let's make this our last question for the day. Thanks for spotting that one. Not a very smart course design to just skip out problems. So this one was about continuity and single-side continuity. It says here, a patient is injected with a drug every 12 hours. Looking at the graph, we see 12-hour increments here. See if we can make that bigger. That's not the best screenshot in the world. It says next that the graph shows concentration of the drug in the bloodstream after T hours. So you can imagine maybe this is insulin or something along those lines. Your insulin pump hits you with 80, I don't know if that's the right amount for insulin, that could be devastating potentially. But whatever the drug is, at time 0, it hits you with some amount. 12 hours later, you have to redose and concentration jumps. But then your liver starts working and everything else with your metabolism until the next injection. So it says here, what values of T does C have discontinuities? That would be at the 12, 24, 36, and 48-hour mark. And for this kind of process, discontinuities are very natural for this kind of function. So they'll be at t equals 12, 24, 36, 48. Goes on to ask further, what type of discontinuity are these? Anyone have a specification for these types? Exactly. These are jump discontinuities. And the question didn't ask this, so let's use the orange pen to make it an official comment. But how about for folks over in Zoom? What kind of discontinuity would you say that is? Or excuse me, what kind of continuity would you call that? Continuous from the left or continuous from the right?
The right?
Exactly. So being ejected every 12 hours in this format is continuity from the right. Let's right here. These are continuous from the right. Well, that kind of ends this one here. Thanks for spotting that one. I appreciate you mentioning it. Any other questions or comments here, folks? Sorry, what was that, Sean? Might have been an open mic, no worries. Any other questions so far? Okay, well, I think I've ran out of material in earnest so far, folks. When we come back to class, we're going to be right here doing our first tangent line, our first derivative computation. So that'll definitely be exciting. Have a nice night, folks, and don't work too hard. If you have questions, I'll be happy to help out.
Really quick, I do have a question actually about the exam next week. So I'm in the group that is going to be taking it at the testing center. Did
The
you say that
Pocatello
we can
testing?
show up anytime during the day on Monday, or do we have to schedule a time in advance?
It's going to be scheduled through them. So here's
Okay.
how it's going to pretty much work. I've initiated contact with the Pocatello Testing Center and got their procedure. What I do is I'm going to send them the exam PDF. I'm going to send them a roster of everyone taking the exam in their testing center and the date that I would like the exam to be taken. Then they're going to reach out to you to schedule a time specifically. If it fills up on a day or something like that, then they'll work something out directly with you. Does that make sense about that process?
Yeah, so just hang tight for now, and I should get something from them soon about scheduling my time.
Exactly, yeah. So I just about have our exam written, and when we come back on Wednesday's class, I'll be sending all that stuff over to the testing center for them to get back with you.
Okay, perfect. Thank you. I appreciate it.
You bet. Have a good one.
You too.